Start recording. Okay. No? No, we're not. Come on. Jerk face. There we go. Oh, now Sean wants in. Okay. Now I think it's stable. Okay, so the first question we're doing is actually almost the entire first question from the 2017 test. Laughing at my jerk face. So we're going to do every single part except for part C, which was a small portion. Come on. Which was a small portion that was actually on thermodynamic stuff. So that's why I pulled it out of there. So the rest of this question is all focused on gases, kinetic molecular theory, and intermolecular forces and stuff. So the question is pretty broken up in terms of what it covers letter by letter. So if you start off looking at the information in the top of the question, the first thing I want to point out is they have provided you with a balanced chemical equation. If they provide you with a balanced chemical equation, in theory, what at some point are you going to have to do with that balanced chemical equation?
Use mole ratio.
Use mole ratio. Okay, so if they give you an equation, all right, so equation means some part of the question will use a mole ratio. So that's one thing when you're looking at these questions to recognize. So then the first part of the text of the question up here, this applies to everything that's there, right? And then each subsection of the question may pull information from that top portion. So just a quick scan of that text, what information did they give you?
Sorry, it's blocking. Temperature and volume.
All right, so you got a temperature and a volume. And what are you automatically seeing that you have to do with that temperature?
Put it in Kelvin.
Put it in Kelvin. So what is that temperature in Kelvin?
393.
Yep. Okay. So you can do that sort of stuff without even having to read the rest of the question. So, but if you see a temperature and a volume, you should already be thinking which formula are you going to have to use. Pervner. All right. So looking at part A, question 1. What are you going to have to do?
Convert volume, like convert liters to moles.
I've got temperature and volume, and what piece of information did they give me in subpart A?
Pressure.
Oh, the pressure.
The pressure. So I've got a P, V, and a T. So you're solving for N. As Jana said, you are using Pervner. So go ahead and set that up. Don't forget, use the correct R off of your formula sheet. Match your R to your pressure units.
Miss Baskin.
Yes.
This is just a math question really quickly, or an algebra question. When I like rearrange the equation, I can just take RT together and put it under PV.
Yep.
Okay, thank you.
Need more coffee. Be back. Okay, so how many sig figs should your answer have?
3.
2.
It is 2 because which of your values has 2 sig figs?
0.40 ATM.
Yep, 0.40 ATM. So for 2 sig figs, what are you getting for the answer? We're still calculating.
Yes, I'm calculating right now.
Uh, 0.31.
Uh-huh.
Yay.
0.31 moles.
That's
Right.
what I got as well.
Okay.
Yeah, me too.
So the second question says, how many grams of carbon disulfide are needed to react completely with that chlorine?
Stoichiometry.
Stoichiometry.
Yeah. Okay.
All right, we said equation means we're going to use the mole ratio. This is the question where you use the mole ratio. So you've got moles of chlorine, and I need grams of carbon disulfide. So 2-step problem. All right, so how many sig figs should you still have in this answer?
2.
2. And what are you guys getting?
7.8 grams.
Depending on what you use for the molar mass, I just added 12 and 32, which is not completely correct. It's 76 point something in there. So 7.8, 7.9, whatever you used is going to factor in there. Now, this would be a question where if you got an incorrect answer here and did not get this point, but you used this number in this location correctly, you would get both points in the second part. So that's what they mean by error carryover. Like if you have to use a number from one problem in another, like you can still, even if you make a mistake somewhere, you can still get all of your points if you do the math correctly afterwards. So, okay.
Miss Baskin.
Yeah, Sean.
I was still kind of writing my numbers down when I think you said this, but like they don't really care if like, so I got 7.9 when I rounded it instead of 7.8. They don't really care about that, right?
Right, because you actually probably used the full molar mass instead of my 32 plus 32 plus 12 that I did in my head.
Okay.
Yeah. That's what, 32.07 plus 32.07 plus 12.01. So, yeah. Okay, so for part B, what information did they give you in part B?
Give you temperature.
Oh, this is where we have to do final minus initial.
No, but they did give you two
No?
temperatures. All right, and then what did they tell you about those two temperatures?
That one is thermodynamically favorable. And the other occurs at an observable rate.
Well, they're both thermodynamically favorable, but what happens at one but doesn't happen at the other?
You can...
For one, no reaction actually occurs, and for the other, the reaction occurs.
So at 30 degrees, no reaction occurs, and at 120 degrees, the reaction happens. That should make logical sense that a reaction will happen at a higher temperature.
Mm-hmm.
And it says why. Explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at the 120. So think about, at a higher temperature, what does that mean for the motion and collision of your individual particles? Go. And while we still don't necessarily have to write complete sentences, you do still need to make sure that your point is clear.
Wait, but didn't last time we say something about how if they're moving too fast, they won't react with each other or something?
No, they won't attract each other. You won't have intermolecular forces.
Oh, okay.
Okay, anybody have an answer that they want to read out?
I can read mine.
All right, Sean.
I said the collisions will happen more frequently because the particles are moving faster, and they will be stronger because they collide at greater speeds.
Okay, so they're occurring more often at greater speeds. How does that affect the rate of the reaction? This is a small tie-in into kinetics, so.
Oh, I didn't think about that part. You said, how does it... Wait, can you say what you said one more time?
So you talked about speed and frequency of collisions. How are those things going to impact the rate of the reaction?
The greater frequency of collisions means more molecules within the thing are reacting, right? Does that make sense, or is that not complete enough?
What they're looking for here is you to describe how this situation allows the reaction to overcome the activation energy. So anytime you
Oh.
see something talking about whether or not a reaction occurs, like that observable rate part
Mm-hmm.
should clue into your head, oh, I should include something about kinetics,
Okay.
right? Observable rate, that is telling me, kinetics. And if I'm thinking kinetics, my barrier in kinetics is called activation energy.
So because they're colliding more and are moving faster, they have more energy to overcome the activation energy?
Yes.
Okay.
Yes. So this is one of those things where it, like they can, because you're going to see another question on another page that sounds very similar, but since they didn't ask anything about rate, you don't have to link it to activation energy. So this is one of those things where it's like, you know the chemistry, like you knew that answer, but you didn't know that that's the answer that they were looking for. So it's those keywords that's part of the reason why we're going through these, is figuring out that, oh, since it says the word observable rate, I need to talk about activation energy in this instance. Annoying. There is another way to kind of see that that's where they're leading you, and that's by looking at this diagram. That is a subpart of this question as well. And since they have that in there, that can maybe also clue you in. But if you look at part B, we know that this year there will not be a question like this, because they have said explicitly that there are no questions that you have to draw a diagram or graph. So you wouldn't have to do this, but you might have to explain it, if not draw it. So this one says the graph below shows a distribution of the collision energies of the molecules at 120. Draw a second curve that shows the distribution at 30. So for something like this, there is nothing on this graph that tells you what this temperature is. You have to pull that from the text, and it is helpful to then be like, oh, the instant you read the phrase, the graph below shows the distribution of the collision energies of reactant molecules at 120, I would write 120 on the graph, just to be like, that's what that is. And then draw it for what it would look like for 30. So really fast, draw what you think it would look like at a lower temperature. What is this? Is a Maxwell-Boltzmann distribution. What does it look like at a lower temperature than this? So remember, you got to think left, right, up, and down. All right, so the first thing, my point here, right? So on a 30-degree graph, is that going to be shifted left or right?
Right.
At 30? 30 is a
left.
lower temperature.
It'd be left.
So it's going to be left.
I see what you're saying.
Lower temperature means fewer collisions. All right. So lower temp equals.
So wait, Ms. Baskin, these ones you have to. So when you said left, right, I didn't realize what you meant. Because I thought, because I just shifted it lower, like it's much shorter. Like I didn't make the top any. Okay, yes. But it also will be shorter, right?
No. Well, shorter where? So 1 point was given for drawing the peak of the graph to the left and above, right?
Oh, because it's like squished?
Yes.
But it won't, but
So
this.
lower temperatures, remember, lower temperatures are squished to the left. Higher temperatures get way stretched out.
Okay. But
then-
this graph has to stop before the activation energy because it doesn't react. There's no reaction.
Well, it doesn't necessarily have to stop, but it does need to be lower than. Yes, absolutely. The second point was for drawing something that crossed that activation line at a lower point.
Okay.
Yeah.
So
So 1 point was given for something that was like squish it into the left, and 1 point was given for something that crossed that activation energy lower than down there. All right, and then I took out part C, so we can just look at D. All right, and this is that you can also produce this in a different equation. The completion of the reaction, a chemist successfully separates CCl4 from oops, I should get back on that. CCl4 from HCl by cooling the mixture to 70 degrees. So at 70, CCl4 condenses while HCl remains a gas. So that's the information they gave you. At 70 degrees, CCl4 condenses while HCl remains a gas. So what does that mean for the state of matter of carbon tetrachloride at 70?
it's a solid.
Not
Or
a
is it
solid.
liquid? It's a liquid.
A liquid.
It's
All right. Condenses means it's become a liquid, where it says HCl remains the gas.
Miss
Okay.
Baskin, what's the term for when something becomes a solid then?
Freezes, or from a gas, it would be deposits.
Okay.
Yeah. Okay, so question number 1, it says identify all types of intermolecular forces present in HCl. This is a 1 point question, and if you don't list them all, you don't get the 1 point. But it should be easy. How many different IMFs does HCl have?
2.
What is the one that you're going to write for literally everything when they ask this question?
London
LDF.
dispersion forces.
London dispersion forces.
Written dispersion forces.
All right, so everybody gets London dispersion forces.
Miss Baskin, I feel like I've asked this before. Do you have to write out London dispersion force, or you keep write LDF?
The first time you write it, you should write London dispersion forces,
Okay.
and then you can put LDF in brackets or in parentheses after it, and then refer to it as LDF after that.
Okay.
What else does HCl have?
Dipole.
Dipole, dipole.
Also,
I can pretty much guarantee you with the structure of what they've told us about this year's test, you're going to have a question exactly like that at some point. So whether they provide you with a structure or give you a simple molecule, like whatever, that is something that the hands down is going to be asked. And then the second question, what can be inferred about the relative strengths of those forces between these two? And note that they did change this to a liquid now. All right. So if I know at 70, this is a liquid and this is a gas, what does that mean for their forces? Who's got stronger ones?
it means that CCl4 has stronger forces.
Yes. So if at 70 degrees Celsius, CCl4 is a liquid, means it has stronger IMFs than HCl, which remains a gas. Did this question ask you to identify what the intermolecular forces for CCl4 are?
Nope.
Nope. If you did, what are they?
Also London dispersion forces.
And only London dispersion forces,
Oh yeah.
right? Because it's nonpolar. So this is kind of And you'll see it again on one of the other questions. They've kind of gotten into the habit of asking these questions where we're so used to thinking of London dispersion forces as the weakest intermolecular force, because it is when you compare them just in similar things. However, London dispersion forces can be overall a stronger intermolecular force when you are comparing two different molecules that are completely different in size, right? There is nothing similar in size between carbon tetrachloride and hydrochloric acid. They have vastly different molar masses, vastly different sizes, and because of that, the London dispersion forces in CCl4 are far stronger than the dipole attractions in HCl. So you have to answer the question based on the data they give you in the problem. And the data in the problem clearly says at 70, this is a liquid, this is a gas. Hands down, all you need to pull from that is liquid has stronger forces than gas. Don't overthink it. The question is designed to have you overthink it. Annoying. All right, so on to the back, where we are going to see a similar sort of thing. So this is the full question 4 from 2018. That's, one of the short questions at the end. So they've given you some structures, right? And they've given you some boiling point data. So this is a much more likely question type than having to draw a structure of some sort. Like, they've given you a structure, they've given you some data. We know the questions this year are going to be like data-based, interpret the data, interpret what it means. So if I am looking at this, before I even read the text of the questions, I look at the information that they've given me. What can I figure out? What does this molecular structure tell me when I look at these two things? Carl? Anybody?
Ms. Baskin,
Yeah.
is it that CS2 is nonpolar and COS is polar?
Yes. Nonpolar, polar, right? So I've got symmetry in the CS2 and I don't in the COS. All right, so you should be able to like quickly pick that up visually. But then if I look at these boiling points, and you got to remember, boiling point means I'm turning from what to a what?
Liquid to gas.
Liquid to gas. So you got to think about, what do those numbers mean, harder versus easier? So for which one of these is it harder to turn into a gas?
CS2.
CS2, right? Higher number equals harder to make gas. And if it's harder to make it a gas, what does that mean for the intermolecular forces?
They're stronger.
They're really
Stronger.
strong.
Okay. So it is often helpful when they give you a data table like this to actually try and just very quickly mentally, whether you write it down or not, but mentally think about what information did they just give me, because they would not give it to you if it wasn't critical to answer the question. So the words of the questions can sometimes be designed to trip you up, but the numbers are just the numbers. So focus on what the numbers say. And the numbers say that CS2 has a higher boiling point, which means it has stronger forces. Now the text of the question says, in terms of the types and relative strengths of all the intermolecular forces in each compound, explain why the boiling point of CS2 is higher than that of COS. So clearly there must be multiple points assigned. Some of those points are in that first phrase. Identify all the molecular forces in each compound. So start there and then explain the second part, which we identified over here onto the right.
Yeah, sorry guys.
So to get the point in the first part of the question, what do you have to identify? Who's got what?
They both have LDF.
Mm-hmm.
And then doesn't CS2 only have LDF?
Correct.
And then COS has dipole.
Mm-hmm.
It's polar.
So, Miss Baskin, I remember
Yeah.
I'm not looking at my notes that I took. I should go get them of like IMFs and stuff.
Mm-hmm.
But for the most part, with polar things, we are mainly gonna see dipole.
Yes.
Okay.
Yeah, hydrogen bonding is going to be a very, very small subset. Almost exclusively, we're going to be talking just LDF and dipole. Okay, so if you listed that information, that would get you 1 point. The second piece of information is simply stating why the boiling point of CS2 is higher than that of COS. So who wants to take a crack at that?
Didn't we already say this?
Yes. So
Okay.
you write it. You
Yeah.
say it.
I won't say it. I said the last 4 things.
I mean, it's basically restating what's over here on the right. So the higher boiling point for CS2 means its IMFs are stronger. Period. It's not asking you to explain why they're stronger. It's just asking you to recognize that they're stronger. It's not asking you to say, it's like, well, it's got more polarizable electrons and it's not asking for all that. It's just saying that clearly the forces must be stronger because its boiling point is higher.
Period.
Done. Don't overwrite. Don't overthink. All right. The next question is clearly going to be a math question because they gave you numbers. So what formula do you need to use?
Hold on, I'm reading.
Is it? I see a volume. I see a temperature. And I see something that could be turned into moles. So is it Pervner?
And it asks about the pressure. Yeah, so it has to be
Yes,
pressure.
asking for P. Yep, so you're going to have to convert that to moles and then plug it in to find P. So, all right, so you do that, plug that in, I get more coffee.
This coffee, Lord, it's been 3 cups.
Right.
Look, sometimes, okay.
Sometimes we need our cups to run it over with the coffee.
You can't be coming for my coffee habit.
By the way, guys, we already did the molar mass for CS2 on the
Oh,
front.
you're right. Thank you, Sean. I was really about to go calculate that
Because
again.
in my head, I was like, we already did this, so I'm not doing it again.
Since it doesn't give us a certain pressure unit to use, which one do we use?
Technically, they would end up accepting any of them,
Okay.
but almost everybody just uses ATM.
And it's already in Kelvin. That's so nice of
I
them.
know. Because it's one of the later questions. So,
If you didn't do it before, then like,
Yeah.
if you did it once, you know, we know you can do it.
mm-hmm.
My nose is running a lot all of a sudden, and I don't know why.
Better
Maybe I
catch
can,
it.
maybe I can smell your cat through the screen.
Aw. She's all just like melty. So cute. Her head's like wedged into the cushions. Aw, look at that puppy head.
He's balancing on a thread. If he moves one wrong way, then he's gonna.
It's really cute, Carl. All right, what are you guys getting for a pressure?
0.69. Would it be 266?
Mm-hmm.
Yes. Yay. ATM.
Yeah, point. Depending on what you used for the molar mass, 0.69 or 0.70.
I was about to say, I was like, my number's always a little off. What's going on, calculator? Acting up.
Okay. So for this question, just to let you know how the points are assigned, doing this conversion was 1 point, and then plugging everything in and getting this answer was the other point. So there we go. Okay, so the last question is also a question 4 from last year's test. So students doing an experiment with CO2. Originally, a sample of this gas is at 299 and 0.70 ATM. Student increases the temp to 425. Describe the effect of raising the temperature on the motion of those molecules. That's straightforward and easy. What happens when you increase the temperature?
They go faster.
They go faster.
Increasing
That's literally it, right? They increase the speed, they go faster, like anything like that. No complete sentence is needed.
Molecule go fast.
Oh no.
I'm gonna just say that molecule go fast. That'll be it.
Okay. Then it says calculate the pressure at 425. We were all a little surprised that they asked this question last year because they have not done something so straightforward in a long time, because this is basically two temperatures and one pressure, and they're asking you for the other pressure. This is like a first year chem sort of gas law problem. It's not a Pervnert problem. The annoying thing is that the equation's not on there.
There.
So what you have to do is you have to remember how to derive this formula, unless you've just happened to have individually memorized Boyle's, Charles, and Gay-Lussac's law, which you shouldn't. No. So this is what we refer to as a change in conditions.
Ooh.
Right? We've changed the conditions.
Got a little toasty.
Uh-huh.
A little hot.
So you should know that if I increase the temperature, what happened to my pressure?
It increases as well.
It also increases. Okay. So if that also increases, then you know what your answer should be. It should be bigger than 0.70.
Mm-hmm.
But when you do this, this is where I said stack Pervnert on top of itself and cross out what they don't mention.
Oh, this was demonic.
This is like the beginning of the summer stuff.
Yeah. Now the other thing is, you can just write the combined gas law on your formula sheet.
What is it? This is that.
No, the combined gas law is technically P1 V1 over T1 equals P2 V2 over T2. Now you'd still see regardless that volume's not mentioned, moles aren't mentioned, and R is a constant, so it cancels out.
Ms. Baskin,
Yes.
would I write that under gases, liquids, and solutions?
Yep.
Okay.
But if
Good.
I need to rearrange this for P2, that's the correct algebra.
This is straight from summer. Oh my god.
Mm-hmm.
This is straight from the pits of hell.
So I will say that while this is not difficult chemistry, because it had been so long since this particular skill level was taught, that a lot of people miss this question. But if that's your formula, plug in your numbers and see what you got.
I just remember so many. I could not do these. I could not do it. Um,
Your temperature's already in Kelvin, so that's easy.
I think this is actually one of the much easier units to understand, though.
Well, that's good. So what are you getting to how many sig figs?
3,
No.
2.
2.70. That zero
Right.
don't count.
So 0.99.
0.99.
yeah, that's all I got.
What?
Okay.
It's
You
bigger.
get 100, Sean? You didn't get 100, Sean?
Don't
Okay.
be rude. Stop being rude.
Okay. Wow.
Okay. C. In terms of kinetic molecular theory, briefly explain why the pressure changes as it is heated. Now, they didn't lead you to say what the change is, but you just calculated what the change is. You predicted up above what the change should be. So why, on a molecular level, right? Kinetic molecular theory means think particles. What are the particles doing that give you this
Do you
increase
need-
in pressure?
Do you need to refer to the container being rigid? Like, because they're banging into the walls?
Mm-hmm. Because that's what pressure is. Yes.
Okay.
All right. So there's two possible ways to explain this. Because there's two ways that temperature affects pressure. What is one way that temperature affects pressure?
It affects the speed.
More collisions.
More collisions.
Right.
All right. So one thing you could say is like there are more collisions at the higher temperature, so there's more pressure. Okay. And what is the other thing? It's not just more collisions, but they're
harder.
They're harder. They're more forceful. They have more energy, whatever you want to say, because they're moving faster, so they're going to have more force. So points were awarded for either one of those explanations. Okay. And then what?
This is a question from me. So, like, if you had, for instance, like, some sort of gas in a balloon, right? And you put that amount of gas into, like, a similarly shaped or similarly sized rigid container, would the pressure inside the rigid container be greater than the balloon because it's, like, harder? Or, like, it's more locked in place? It has no give to it?
No, as long as they're at the same conditions. But if you started trying to change either, like the temperature, the pressure inside the balloon would not change because it is flexible, but the pressure inside the rigid thing would.
Okay.
Yeah. Okay, and then the last one, the student measures the actual pressure and observes that it is less. So the actual pressure is less than the pressure predicted by the ideal gas law. Explain why.
Because nothing is ideal in this
Well,
world.
I know, but so explain what is the thing that matters the most here.
Well, I'm gonna just say that nothing is ideal, and that'll be the point.
Uh-huh.
This is the
Less pressure is caused by which of the factors?
Greater volume.
No.
Nope. Oh, because we're not dealing with volume.
Mm-hmm. Because there was
Less-
two ways that that real gases are not ideal. One was the volume, and what was the other one?
Attraction.
Attraction.
of each other.
Okay. So CO2 has attractions between the molecules, which decrease, right? That's an arrow, decrease the pressure. There you go. Okay, so with all of that, we're done with the Unit 3 wrap up. So go do your stuff on College Board, on AP Classroom for that. Then Unit 4 is, which will start on Friday, is the last one that pulls stuff from first year, from sophomore year, and from bits and pieces of this year. So that's where we're going to review oxidation reduction, which was last year, but also titration, which we did way at the beginning of this year, that sort of thing. Okay.
So, Ms. Baskin, with the due dates of stuff,
Mhm.
Unit 3 stuff is due Friday?
Yeah.
Okay.
Yeah.
Okay, cute. Ms. Baskin, you see I shaved my head?
I know. You see, I haven't yet.
Yeah, I couldn't handle it anymore.
I mean, I can't
And you
either.
look great.
But...
I broke. I just said zzz.
So, all right,
Thank you.
I gotta kick you guys out so I can process this video and go to the bathroom before my next class in 5
All
minutes.
that coffee.
Yeah.
My arm looks
Bye, Miss Baskin.
Bye.
Thank you.
Uh-huh.